Howdy, welcome to Elementary Statistics. I'm Lance Curtis, and this is the lecture for Section 12.1, One-Way ANOVA. Here in this lecture, we're going to be looking again at the F distribution because a good portion of our analysis method is based on the F distribution. We'll then get into the particulars of one-way ANOVA, including a look at the requirements, calculating the test statistic, the critical value, and also how this affects the design of experiments. We'll then be looking at wrapping up our lecture with a look at identifying which means are different, and specifically we'll take a look at the Bonferroni test. So here in this method, here in this section, we're going to be introducing a method of one-way analysis of variance. And this is what the acronym ANOVA stands for. ANOVA, which is analysis of variance. We're using one-way ANOVA to test hypotheses that three or more population means are all equal. So when we were looking at chapters 7 and 8, we were basically looking at testing claims with respect to one sample. And then we moved on to chapter 9, where we talked about extending those claims to two samples. And now, here in chapter 12, we're extending that out to three samples or more. So we can have 4, 5, 6, 7, however many we want. Now, because the calculations become very complicated once you go past two samples, we're going to be looking at using technology to obtain the results from our analysis. First, let's go back and review what we've learned previously about the F distribution, because our analysis method is based on the F distribution. So our method for testing claims about one population, standard deviation or variance used the chi-square distribution. And then we moved on to two population standard deviations or variances, and we use the F distribution in that instance. We're going to be looking again at the F distribution. It's skewed, as the statisticians would say, to the right, because that's where the larger tail is. And it's skewed even more than the chi-square distribution. Just like the chi-square distribution, our density curve is always in the positive region of our horizontal axis. F values are always positive. However, unlike the chi-square distribution, the F distribution has 2 degrees of freedom. Let's talk for a moment about one-way ANOVA. One-way analysis of variance is simply a method of testing the equality of 3 or more population means, and we do this by analyzing sample variances. This particular method of analysis is used with data categorized with one factor, and we call that factor a treatment. So in effect, what we have is one characteristic that's used to separate sample data into different categories. Now, the hypothesis testing for ANOVA always starts with the same foundation. First, our claim is always going to be that each of the population means are equal. So however many populations we're looking at, how many different groupings we want to examine, that's the number of population means that we set equal to each other. And we separate them out with subscripts, 1, 2, 3, and so forth. So our null hypothesis is going to be that all of these population means are equal to each other. Null hypothesis, as always, is a statement of equality. But since this was our claim, that all the population means are equal, that means our null hypothesis, our alternative hypothesis is going to be that at least one population mean is different from the others. When we think about this, it makes sense there's one population mean that's not equal to the others. It could be 1, it could be 2, it could be more. It just depends on what populations it is that we're looking at. So when you think about this, it really actually kind of makes sense. In essence, our claim is that none of the population means are different. If everything's the same, then none of them are different. And of course, we learned earlier in the course that the complement of none is at least 1. So the complement of none being different is that there is at least one that is different from the others. Now we're going to be using technology to calculate our test statistic and p-value, because doing the calculations by hand is quite complicated. However, many of the same conventions that we used before we'll be using again here. Let's talk for a minute about requirements, because our methodology is based on certain assumptions, and that means we must first meet certain requirements in order to apply it. So the first requirement we have is that the populations have distributions that are approximately normal. Second, the populations have the same variance or standard deviation. The samples are simple random samples of quantitative data, and the samples are independent of each other. Finally, the different samples come from populations that are categorized in only one way. Keep in mind that the hypothesis test under our methodology is right-tailed. It doesn't seem like it because there really was no inequality sign with our alternative hypothesis in the way that we're accustomed to seeing it. It's simply the words that at least one of the sample means at least one of the population means is different. So it's not intuitive that our methodology is right-tailed, but yeah, keep in mind we are running a one-tailed hypothesis test on the right, which is a right-tailed test. Now, the reason for this design is that it allows only large values of the test statistic, or accordingly small p-values, to result in rejection of the null hypothesis. This, in essence, what we're doing is we're decreasing the probability of a type 1 error, where we fail to reject the null hypothesis even though we should. Keep in mind the test statistic is the boundary of the critical region underneath our distribution curve. The p-value itself is the area of that critical region under the distribution curve. Our test statistic is going to be an F-score, and it's calculated as you see here. We take the variance between the samples, and we divide it by the variance within the samples. The variance between the samples we can express as the sample size multiplied by the sample variance whereas the variance within samples is measured by the pooled sample variance. Note that the estimate of variance we have in our denominator depends only on the sample variances. It's not affected by differences among the sample means. That's not true of the estimate of variance in the numerator. It is affected by differences among sample means. We also need to understand that the F-test statistic is very sensitive to sample means, even though it's obtained through two different estimates of the common population variance. Now we find critical values by assuming a right-tailed test based on the F distribution. So for k samples, each having identical sample size n, we have all the sample sizes equal to each other. The F-curve will then have degrees of freedom in the numerator equal to k minus 1, where k is the number of different samples or groupings, and degrees of freedom in the denominator of k times the quantity n minus 1. If our sample sizes are unequal, then we're simply going to use a weighted measure to account for the different sample sizes. Let's take a look at an example in which this can be applied. We've looked previously at an example of levels of lead in the blood compared with the performance on IQ tests. So here we have performance IQ scores and the significance level of 5%, and we're asked to test the claim that the three samples, low blood level, medium blood level, and high blood level, come from populations with means that are all equal. Notice that our sample sizes are not the same. The sample for low blood lead level is much larger than that for medium and high blood lead levels, respectively. That's not a problem for one-way ANOVA, as we'll see shortly. However, before we use our method, we need to check that our requirements have been met. So, if we were to make normal quantile plots for each of the three samples, we would see that they each have an approximately normal distribution. So that meets our first requirement. Second, the three samples in our table have standard deviations that are not dramatically different from each other. So we could say that the population variances appear to be about the same. We can say this because variance is an unbiased estimator. The sample variance tends to be the point estimate. It targets well the population variance. So if the standard deviations are not dramatically different, then neither will be the sample variances, and we can then infer from that that the three population variances are going to be about the same as well. Looking at the way the study was designed, we can simply say that the simple random samples are what we have for samples. We also know the samples are independent of each other. The performance IQ scores are not matched in any way, so we don't have any dependency between samples. And last, there's a single factor that's separating each of the different samples, and that is the level of lead in the blood. So it appears our requirements have been met. What are our hypotheses for our hypothesis test? First, we think about the claim being made. In the case of one-way ANOVA, the claim is always the same, that the mean population means are the same. So we're going to say that the mean IQ scores from the three different populations are the same. So mu1 equals mu2 equals mu3. Remember, the null hypothesis is by definition a state of equality. So we're going to set each of the three population means equal to each other. But this was our claim, and so we can't adopt the claim for our alternative hypothesis, and so in this case we have to take the complement, and that will be that at least one mean is different from the rest. So this is what we'll always see with one-way ANOVA. The claim will be that all the population means are equal. The null hypothesis will be that all the mean populations are equal. And the alternative hypothesis will be that at least one of those means is different from the rest. Notice we have a mismatch between our alternative hypothesis and our claim. Now, it's not really apparent because we're using words and not mathematical symbols. But what we do have is a right-tailed test. Now we've set up our hypotheses, let's prepare to test our claim. The first thing we're going to need to do is to calculate the test statistic. So once we're in data, once the data is in StatCrunch, go to Stat ANOVA one way. When you get to the options window, select the columns that you want to analyze, and then go down to the bottom of the window and press Compute. A results window will appear with two tables. The table on top lists column statistics. The table on the bottom is our ANOVA table, which contains the results of our ANOVA analysis. The test result comes right off the result window in the ANOVA table. As always, the second to last value that's listed. The p-value, as always, is the last value listed. So again, in the ANOVA table, the last value listed is the p-value. Now, there's several options for conducting ANOVA testing in StatCrunch, but for most of what you're going to be doing with it, working your assignments for the course, the default settings will be just fine. So there's no need to adjust anything. Pretty much it's just select your data columns, press Compute, and away you go. Now we can decide whether to reject the null hypothesis. Remember, if we're inside the critical region, we're going to reject H0. If we're outside the critical region, we fail to reject H0. Again, our test is based on the F distribution. So here I have the F calculator from StatCrunch. I put in the respective degrees of freedom for the numerator and the denominator. And then I'm putting in my alpha level of 5% for my area. That's the area of my critical region. And I find that my critical value is 3.02. Going back to the results window from our ANOVA analysis, there in the ANOVA table, I can see that my p-value is 0.0195. So I compare that with my significance level, and I find that I'm inside the rejection region. Therefore, I'm going to reject H0. Alternatively, I could look at my test statistic, 4.07, and that's going to put me well inside my rejection region. So 4.07 is about right here. So that's definitely inside this region of rejection, and that's going to lead me to the same conclusion, reject the null hypothesis. What do you conclude from the hypothesis test? Well, again, we're going to go through the same four options that we typically see with this question. However, we can ascertain that the first question we ask is, did we reject H0 or did we fail to reject H0? In this case, we rejected H0, therefore there is sufficient evidence. So I'm looking at answer options C and D. The next question we ask is there a match between our alternative hypothesis and our claim? In this case, there is not a match, and therefore we're going to say warrant rejection of the claim. So the answer option that we're going to select is answer option D. Now, there's some things to note about one-way ANOVA hypothesis testing. Because the claim is always the same, the null hypothesis is always the same, the alternative hypothesis is always the same. So we're never going to say that we support the claim. We're always going to say warrant rejection of the claim. So then the only real question is, do we have sufficient evidence or did we not? And the answer to that question is going to be the same as did we reject H0? If we did reject H0, then we're going to say we have sufficient evidence. If we did not reject H0, meaning we failed to reject H0, then that's going to say that we have insufficient evidence or we do not have sufficient evidence. There's some cautions that we need to make about conclusions with this methodology. In this particular case, we rejected our null hypothesis. That means we have sufficient evidence to conclude that the three population mean scores are identical. Had we failed to reject H0, we could conclude that at least one of the population means was different from the others. However, one way ANOVA doesn't tell us which of those means is the different one. It also doesn't tell us if there's more than one. So perhaps we're looking at, say, 5 populations, and so we say that 5 population means are equal to each other. Well, if we fail to reject H0, that tells us that there's at least one of the population means that's different. Well, we just can't say which one it is, or even if there's more than one. That said, let's take a look back at our results window from StatCrunch. So here we have our ANOVA table and also the column statistics table for the data used to produce the ANOVA table. If we look at our sample means, we can observe that the mean value for the low sample is greater than that for the medium or the high samples, which, for all practical purposes are identical. 94.14 is not the same as 94.19, but they're not that far apart. This means we can informally conclude that lead levels above the low level appear to have an effect on IQ scores. When it comes to designing experiments, we keep adding more and more populations to our test, and so what that does is it creates an increase in the potential influence of extraneous factors on our results. Naturally, we want to reduce this effect as much as possible. So here are 2 design approaches that have worked well in that regard. The first is that we can have a completely randomized design. What this means is that each sample value has the same chance of belonging to the different factor groups. We can also use a rigorously controlled design. What this means is that we choose sample values carefully so that all other factors have no variability. Now, as I mentioned just a moment ago, ANOVA hypothesis testing can tell us if at least one of our population means is different from the others. What it can't do is identify which one. And it can't even tell us if there's more than one. All it can say is that there's at least one. So what we can do is use informal and formal methods to determine which of the means is the deviant. Some informal methods for comparing means include constructing box plots of the different samples and then examining them to see if there's any overlap between the box plots. Speaking of overlap, we can construct confidence interval estimates for the means, and then we can compare those intervals to see if any of them don't overlap with each other. More formal methods for comparing means include using range tests. These allow us to identify subsets of means that are not significantly different from each other. We can also use multiple comparison tests, which basically take pairs of groupings, and we're going to take the means for those groupings that we're pairing together and examine them a pair at a time. But we end up having to make adjustments to various values in our hypothesis test in order to avoid the problem of having an alpha that increases as the number of individual tests increase. So we're going to have to make some adjustments along the way in order to avoid that increasing significance level. Now, there's a popular approach known as the Bonferroni comparison test, which is a type of multiple comparison test. And it's rather more popular than its counterparts. So we're going to be talking here about Bonferroni multiple comparison test. Now, the way this works is that we actually make the different pairs of samples. So grouping 1 with grouping 2, grouping 1 with grouping 3, grouping 2 with grouping 3, so on and so forth. And for each of these groupings, we're going to perform the following steps. First is we're going to form a separate null hypothesis for each possible pairing of two samples. The claim and the alternative hypothesis remain unchanged. Here's our test statistic, which is a t-score, and it's calculated according to this formula here. Note that MS error in the denominator is the mean squared error. We take that from our ANOVA table. It results from all of the available sample data. Next step is to find the critical value, or the p-value, make the appropriate adjustments, and then we'll be ready to resolve our hypothesis test. Now, the critical value is simply the boundary of the critical region with area alpha under the student t distribution. The methodology we've been using before is based on the F distribution. Now we're back to actually basing our method on the t distribution. That's Bonferroni. The p-value is going to be a two-tailed area under the student t distribution bounded by the test statistic. But you have to multiply the p-value by the number of possible pairings of two samples. In either case, we're going to take degrees of freedom as being the total sample size of all the samples together and subtracted by the number of groupings. And then, at this point, we simply resolve the hypothesis test using the standard conventions with which we are familiar. Let's revisit the example that we saw earlier, where we looked at lead levels in the blood of individuals who were taking IQ tests, and we're comparing the lead level in the blood with how they scored on the IQ test. We rejected the null hypothesis and concluded we do have sufficient evidence to reject the claim, meaning that at least one population mean is different from the others. What we want to know now is which of those population means is the different one. To this end, we're going to use the same data and construct a Bonferroni test with a 5% significance level. Note that StatCrunch doesn't have any direct option for performing this test, so there's going to be some hand calculation involved. However, StatCrunch becomes useful even in this instance because we can use StatCrunch to make our ANOVA table and then take the values out of our ANOVA table and use them for our calculation purposes. So, to start off with, what are our hypotheses? Well, if we think about the claim being made, in this instance, the mean IQ scores from three different populations are going to be the same. Remember, the null hypothesis is by definition a statement of equality. Here we actually have three null hypotheses, one for each possible pairing of population means. So we could pair the first two groups together, or we could compare the second and the third group together, or we can pair up the first and the third together. So we have three different pairings for three population means for which we're performing hypothesis testing. Typically, we're going to want to reflect the claim in our alternative hypothesis. In this case, we can't do that because our claim has equality. In fact, our claim is a statement of equality. Equality goes with the null hypothesis. So we're going to have to take the complement of none of the population means being different, and that's going to be that at least one of those means is different from the rest. Remember, we're comparing pairs of groupings, and so we'll have to proceed this procedure with each of the null hypotheses that you see here at the top. what is our test statistic? Well, go back to our ANOVA table. We have values here that we can use to calculate our test statistic. You would think that the test statistic comes from the ANOVA table, but it doesn't. It's not the one you want for Bonferroni. For Bonferroni, you have to calculate your test statistic according to the equation given. And this is the equation you need. So you substitute values in for each of these numbers. Notice how we're taking values out of our results window and using it for our calculation. So we can get the sample sizes for samples 1 and 2 from the column statistics up above. We can also get the sample means from that same table. So we're subtracting sample means in the numerator, and then in the denominator we've got sample size, and we've also got MS error, the mean squared error, which if you look at your ANOVA table, you can find that pretty readily by looking at the error, mean squared error, not mean squared columns, mean squared error. So we just take that number and substitute it into our equation, and now it's just a matter of punching this out on our calculator, which when we do, we get 2.2521. This then is our test statistic. What is the p-value? Well, our p-value, again, we're going to use values from our ANOVA table. You would think that we could just take the p-value from the ANOVA table, but no, when you're doing Bonferroni, you can't just take the p-value from the table. You have to actually calculate it based on the test statistic. So we're going to use our test statistic to calculate our p-value. Remember, the p-value is the area under the curve bounded by the test statistic. Bonferroni is based on the t-distribution. So we use the t-calculator in StatCrunch, put in our test statistic for our horizontal axis value, put in the appropriate degrees of freedom, and out comes the area under the curve, which is our p-value. However, this is only for one pairing. So in order to reduce the risk associated with an increasing significance level that comes from performing multiple paired tests, what we're going to do is we're going to take this p-value and we're going to multiply it. We're going to adjust it by multiplying it by the number of possible pairings in our groups. So 3 different groups means that we have 3 possible pairings. So we're going to take that p-value there from that I calculated as the area under the curve, and I'm going to adjust it by multiplying it by 3. 3 because there are 3 possible pairings. We have 3 groupings. I can group groups 1 and 2 together. I can group groups 1 and 3 together, and I can group groups 2 and 3 together. It's 3 possible pairings. When I do that multiplication, I get 0.0392. This then is the actual p-value that I'm going to use to resolve my hypothesis test with Bonferroni. Now we're ready to decide whether to reject the null hypothesis. Remember, if we're inside the critical region, we reject H0. If we're outside the critical region, we fail to reject H0. Let's take a look at the p-value we just calculated, 0.0392. If I take that p-value and compare it with my alpha level, I can resolve the test. Before I do that, I want to make mention of how I actually calculated degrees of freedom, because you may be wondering, how do I get 118 degrees of freedom? Well, for Bonferroni, the degrees of freedom is calculated by the total sample size. So you take the sample sizes for each of the different groupings and add them together. So that gives us 121. And then we subtract from that the total number of groupings that we can have, which in this case is 3. So we're left with 118 degrees of freedom. If I compare my p-value with my significance level, I find that I can fit the area for the p-value inside the area of my rejection region, which is alpha, and that means I reject H0. If I wanted to compare the test statistic with a critical value, I first have to get the critical value. And I can get that by dividing alpha by the number of possible pairings for my groupings. So our alpha level, significance level of 5%, we divide that by 3, and that gives us 1/60. We then put that into the area portion of our t-calculator, and we calculate out a critical value of 2.15. Now when I compare my test statistic with this critical value, I find that I'm within the region of rejection, and therefore I'm going to reject H0. So no matter which way you go, you're going to find the same conclusion. What conclusion do we make from our hypothesis test? Well, did we reject or fail to reject H0? In this instance, we rejected H0. Therefore, there is sufficient evidence. And since the claim and the alternative hypothesis never change, and there's a mismatch between them, we're going to select answer option D. There is sufficient evidence to warrant rejection of the claim that the 3 samples come from populations that all have the same mean. So, with one-way ANOVA hypothesis testing, again, we're not going to have to worry about supporting or rejecting the claim. It's always going to be warrant rejection of the claim. The only question we have to ask is there sufficient evidence or is there not sufficient evidence? And that's the same answer to did we or did we not reject the null hypothesis. So, wrapping everything up, if we reject H0, that means we have sufficient evidence to reject the claim that each of the population means is equal. This means at least one of the means is not equal to the others. Now, reaching that conclusion on one pair for the Bonferroni test is not the end. We need to complete the same procedure for each of the other given pairs. So in this case, if we wanted to bring this to conclusion, we would do the same procedure on each of the other 2 pairs remaining. However, we can also make informal conclusions that in some cases can be just as valid as the more formal Bonferroni testing method. Let's go back to our results window in StatCrunch and take a look at the sample means. So here's our results window from StatCrunch, and if we compare the sample means listed in the summary table located above the ANOVA table, what we find is that for groups 2 and 3, the sample mean is almost identical, but it's the first sample mean that's significantly different from the others. So it appears that the low lead group is somehow isolated from the other 2. So this means we can informally conclude, as we did previously, that blood lead levels higher than a low level will influence IQ scores. Note that we can also compare confidence intervals for each of the pairings, and this provides another option for making an informal conclusion. That brings us to the end of this lecture. If you have any questions, you know what to do. Otherwise, I'll see you in class or the next video. Thanks for watching.